Okay. Now for the next theorem that we're going to go over, it has to do with the concept of continuity and differentiability. And notice that here, this thing does have a derivative everywhere except at this point. Now at this point, it doesn't have a derivative, but it is still continuous. And so we do have this theorem here that states if f has a derivative at x equals c, then f is continuous at x equals c. And so what this theorem implies is that differentiability implies continuity. Okay. Now be very careful because this is not the case in the opposite, so not vice versa. So continuity does not imply differentiability. All right, so let's take a look at what this theorem means. If I go back to a basic function like so, right? And one way to tell whether a function is differentiable from a graph is whether or not it's smooth. Because if it's smooth, then you always have a point where the tangent lines are quickly. So in this example back here, let me rephrase that. The reason this wasn't differentiable is because we had a tangent line with a certain slope, and then at the moment we got to x equals 3, it all of a sudden changed right away. And so that's what creates the issue of not being differentiable here. So if you're smooth, then it is differentiable. And so we can say that if a function is differentiable, then it has to be continuous. But we have shown that if it's continuous, then it's not necessarily differentiable. One other note is in pre-calculus, we said that a function is continuous, and then we would say, for example, a polynomial was smooth, because we didn't have a better word for that. But now we can say, for example, that a polynomial is not only continuous, but it is also differentiable. So differentiable is really the word that we should be using to indicate that a function is kind of smooth throughout its whole domain. Let's take a look at the 4 cases when a function will not have a derivative. So there are 4 cases when a function will not have a derivative. Okay, so case number 1 we've already looked at. It's a corner. And so that's, for example, you come in and then it just changes direction like that. The absolute value had a corner. And again, the issue is we come in with one derivative and all of a sudden it switches to another slope of a tangent line, and you can't have that. So this is continuous, but not differentiable. The second one is a cusp. So an example of a cusp would be if we had a function here and it came in, comes back out. Okay, so in this case, what happens is we're coming in, we hit a certain tangent line, and then it stops and it goes back the direction it came. That's a cusp. Number 3 is a discontinuity. Okay, so that's where you have something like this. Okay, and then the 4th one, let's see if I can fit it in here, would be a vertical tangent. So in this one, what's going to happen is we have a function, we're coming up, and then at some point it goes straight up and down and comes over. Okay. Now at this point here where it's straight up and down, we have a vertical tangent. And when you have a vertical line, the slope is undefined, so it can't have a derivative. So in this case, a vertical tangent has an undefined slope. So a vertical tangent has an undefined slope. Okay. So there are the cases where you can just look at a graph and know, well, that's not going to be differentiable. Of course, when you have to show it, you got to use our left hand and right hand derivatives to do that. But at least you know that it's not supposed to be, so you can figure out you can work on how to figure that out.